So let me say about something about Ramanujan's tau function. So Ramanujan kind of almost a century ago stumbled on a very important function, and this function has received considerable attention now. So if you take the infinite product take this infinite product, okay, just expand it as a power series in X. You'll start off and you'll get some power series in X, and the nth coefficient Ramanujan denoted as tau n. Okay, and he made a bunch of conjectures. The first conjecture was that tau of n times tau of m is tau of n and m, whenever m and n are relatively prime. And the second conjecture was that tau of p to the a plus 1 was tau of p times tau of p to the a minus p to the 11 tau of p to the a minus 1 for every prime p. P is prime. A is bigger than or equal to. I guess it's a is bigger than or equal to 1. I think it should be okay. And 3 is that tau of p is always less than 2 times p to the 11 halves. So these were the conjectures that Ramanujan made in his 1916 paper. Okay? And these numbers, this function, you can calculate them. I mean, Ramanujan wrote down hundreds of them. And, before he made these conjectures, I guess he was looking at some numerical evidence in support of his conjecture. And they're very interesting numbers. They're natural numbers, of course, integers. They could be positive or negative. And shortly after he made his conjectures, these two conjectures were proved by Mordell. But Mordell, I suppose, didn't see that there was a general theory behind all this, and that was left to Erich Hecke to work out. And so Hecke so Mordell in 1917, and then Hecke in 1936, actually, 20 years after, worked out a general theory in which these two things were explained from a theoretical perspective, why they work. Why do you expect this multiplicative property all of a sudden just because of this stuff? Why should there be some sort of recursion relation like this? The third conjecture, of course, was the real doozy, and nobody really knew what this was all about. Until the 1950s, people started, people attempted in various ways of trying to prove the conjecture, but perhaps conceptual insight as to what the conjecture really means didn't open up until the late 1950s and early 60s, when a bunch of people, beginning with, I suppose, Eichler, Ihara, Igusa, a bunch of people, maybe I don't know the complete list of people here, started to realize that this was connected to the Weil conjectures. That same Weil conjectures that I talked about with the Hyperkloosterman sums. So a link to the Weil conjectures. See, again, you would never dream that this is the connected to these type of things. I mean, how mathematics is intertwined is really always kind of the beauty of mathematics. There are lots of surprises. So the Weil conjectures all of a sudden appear, and the link was made in the 1960s. And when Deligne proved the Weil conjectures, this came out as a consequence. And as far as I know, to this day, no one knows how to prove this except through this way of algebraic geometry and Weil conjectures. Now, however, Langlands suggested a method of trying to understand the sequence. So this, as I said, if you're trying to understand numbers, a natural thing to do is to study these so-called moments. So it may be interesting to study what are called moments of the tau function. So Langlands. Well, suggested that we can kind of perhaps look at these objects. Because, as I said, the philosophy in analytic number theory is if I give you a sequence of numbers, you try to understand them. One of the ways of trying to understand them is by studying these moments of these. Well, it turns out that when k equals 1, the study of this series really goes back to Hecke's work, the Hecke theory. For k equals 2, this was studied in the 1939, 1940 by Rankin and Selberg. And for k equals 3, 4, and 5, it is now known that this object has an analytic continuation functional equation, just like the Riemann. It's starting to look like the Riemann zeta function. These things behave like the Riemann zeta function in certain aspects. They have Euler product, they have functional equation, they have analytic continuation, all sorts of interesting things. So for k equals 3, I'm not up to date on my record, but maybe up to something or other, up to certainly not more than 9, I think. We do know about these series, and they turn out to be interestingly fascinating, and they have analytic continuation functional equation. Now, because of the last conjecture, we could do the same Gauss sum kind of approach. So you can take your number tau of p, and you can now divide out by 2 times p to the 11 halves, and that's a number between -1 and 1. And so you can write that as some cosine of some angle, right? And then the question is, as p varies, how do these angles distribute? Are they uniformly distributed? Are they equidistributed? Or are they not equidistributed? Okay, this is the question. So for a long time, people thought that in order to answer this question, you kind of had to go through this machine and get the whole mess. But it turns out that experimental evidence suggested that these things are not equidistributed, but they're equidistributed with respect to another measure. You have to put another measure on the something like 2 over pi, something like this, dx. Instead of the Lebesgue measure, you should put this measure. And numerical evidence suggests that that's the measure that you should be using to study the distribution of these angles. These angles then become equidistributed with respect to that measure. Remember what equidistributed with respect to a measure means. You take a measurable function or a continuous function, you evaluate it on those angles, and then you take the sum and the limit, and it should go to the integral. Well, the integral was with respect to the Lebesgue measure, but now if you tack on this extra fudge factor, it turns out that that's probably the measure that should work. And this was called the Sato Tate conjecture. Because Sato and Tate made this conjecture independently, and they were led to it from various directions. And the miraculous event that took place a couple of years ago is that this is now a theorem. This is now a theorem due to Barnett-Lamb Ghirotti, Harris, and Taylor. I hope I haven't left out anybody else. But bunch of people. It comes out, surprisingly, it's kind of like the post-Wiles developments. You see the opening of the door of modularity conjectures of Wiles and Fermat's last theorem. You have to push that even further and establish a few more modularity results. Once you do that, there's very nice analytic tricks. A good chunk of the final segment here is the Tauberian theorem. Non-vanishing of L functions finally gives you equidistribution. So this gives you some idea of how number theory has been evolving, especially analytic number theory in its relation to other parts of mathematics, especially to algebraic geometry, algebraic number theory, and representation theory. All of that stuff seems to be kind of, the grand synthesis is still in the offing, but clearly the whole field is sufficiently rich that there's a lot of work to be done, and perhaps some of you can contribute to that. Okay, so voila.